Welcome everyone. Today's lesson is going to be about double replacement reactions. We have seen synthesis, decomposition, single replacement, and combustion. One of the things those reactions had in common is that they were driven by a transfer of electrons. They are oxidation reduction reactions. A double replacement does not fall under that category. Instead, a double replacement is driven by either the formation of a solid, a liquid, or a gas. What we're going to do is we're going to divide that into three components here. Those reactions that are driven by the formation of a solid are known as precipitation reactions. A precipitate is when a solid forms from solution. Another type of double replacement is known as an acid-base reaction, also known as a neutralization reaction, and that one's driven by the formation of a liquid. Specifically, the liquid in this case is water. Water is made when an acid and a base neutralize each other. And then the third one is driven by the formation of a gas, and those are known as gas evolution reactions. First, let's take a look at generally what a double replacement reaction looks like, and then we'll break down the three types. You can see the general formula for a double replacement here. Notice we can think of the analogy as if they were two couples dancing and they switch partners. What you'll notice is that the ions of the two compounds, what they do is they exchange places in aqueous solutions and you form two new compounds. Now, one thing that you should notice, there's a pattern here. You'll notice A represents the positive ion, whereas X is the negative ion, or A is a metal and X is a nonmetal. And that would be one compound. Here's the second compound, the same thing. B is the metal, Y is the nonmetal. Metals are always written first. And the general formula is kind of like FOIL in math, that the outers are going to get together and the inners get together. So A and Y, this metal and this nonmetal, will get together and form one compound. And then when the other two compounds form, you need to remember that B is written first because it's the metal or the positive ion. So that one goes first, and that would be the second compound. Now, in order to determine if it's a precipitation reaction, we must use the solubility rules. So on the following here, I have some examples where these two fall under precipitation reactions. Now, notice how in the first example down here, you'll see that lead and iodine are going to get together, forming PbI2 or lead 2 iodide. The reason or the way we got that is because lead is a +2 form, iodine is -1. You crisscross and you get PbI2. And then notice how the inners get together, potassium and nitrate. And again, potassium is the metal, it's +1. Nitrate is a polyatomic having a negative charge. And when you crisscross that, you get KNO3. And then the rest of it was due to balancing. But here is the precipitate. Once you get the two products, you use the solubility rules, and when iodine, which is a halogen, is with lead, it's a precipitate. The potassium nitrate is soluble, and that's why you see the AQ for aqueous, because pretty much anything with the anything with a nitrate or anything with an alkali metal, they're always soluble. Now, take a look at the second example. We have here H2S reacting with iron 2 chloride. Again, the H and the Cl are going to get together. When you crisscross that, you get HCl that you see here. And then the inners are going to get together. Okay. Now, Fe is +2. You could tell by uncrisscrossing it from FeCl2. And sulfur has to go second because it's the negative ion, and that one's -2. When you crisscross, the 2's cancel, and that's how you get FeS. When you look at the solubility rules, as long as chlorine is not with lead, mercury, or silver, it's soluble, so that's why that one's AQ. However, FeS is using the sulfide rule. Sulfur will not be soluble if it's not with either an alkali metal, ammonium, the polyatomic, or the last three alkaline earth metals, which is strontium, barium, and calcium. So you could see here that FeS is going to be a precipitate. All right, let's take a look at the second type of double replacement. This is called an acid-base reaction, also known as a neutralization reaction. And it's the same thing, same format, whereas one of the compounds is an acid. Most acids begin with the letter H. The other compound is a base. Most bases have OH. And when an acid and a base react, you're going to see that salt and water are the products. Now, the fact that water is being made, which is a liquid, this is what drives the reaction. Now, how did we get this? Same thing. You get the outers and the inners, so H and OH are going to get together and form HOH when you crisscross that. And we can simply copy HOH as H2O, and that's exactly what we did here, and it's a liquid automatically. And then sodium and chlorine get together. Sodium is +1, chlorine is -1. And again, when you crisscross that, you get NaCl. And this one happens to already be balanced. NaCl, if you use the solubility rules, as long as you got an alkali metal present, it's soluble. And then water is your liquid, and that's what drives this reaction. All right, here's some common acids. Notice they start with the letter H. Here are some common bases. So if you see these two reacting with each other, you're going to get your salt and your water. And the water is what drives the reaction. All right, let's go over here to the third type. There's a third type of double replacement where a gas is made. Now, we just learned that if you see water made, you automatically put liquid. And that's something we've memorized throughout the years. Well, here's one that if it's made, you're going to put a gas. If you see that hydrogen sulfide is made as a product, you're automatically going to put G for gas. That's made directly. Now, the other three gases that we are going to look at are not made directly. They're actually made from an intermediate product, which I'm putting a square here. These three things that you see here, they are unstable. And as a result, they break apart and generate these gases. Why don't we start with, we'll look at each of the three. Let's start with the carbonates, okay? So if you see that you generate carbonic acid, H2CO3, this is unstable, okay? Now, one of the things you'll notice, I'm going to actually write all three here. The next one will be a sulfite, okay? So I'm going to put here H2SO3, okay? And I'm going to show you the third one is the ammonium ion. So I'm going to go ahead and put here ammonium with, if you look here, ammonium hydroxide is the example. So here I'm going to show you if these three are made, they are unstable. They're going to split up. They're going to decompose into two things. Now, here's a great way to remember this. One of the things that they all make, and let me fix this over here. This looks sloppy. One of the things that they all do when they break apart is they all generate water as one of the products. But the other product is a gas. Because this gas is being made, not only will you see bubbles or fizzing when the reaction occurs, but you will also, the fact that a gas is being made, it will drive the reaction. Well, I want you to do the process of elimination. Water already used up the 2 H's in H2CO3 and one of the oxygens. So just by the process of elimination, you have a carbon left, and out of those 3 oxygens, one's already in the water. So here are the other 2 left, and there's your gas, your CO2 gas that's made. Do the same thing with the next 2 examples. H2SO3, the H's are in the water, one of the oxygens is in the water, so what's left is the sulfur and 2 out of the 3 oxygens, and that's sulfur dioxide gas, which is also another gas that drives this reaction. And then the last one, you'll notice there are 5 hydrogens, okay? 2 of them go into the water. The only oxygen you see there goes to the water. So what's left is the nitrogen, and there's 5 hydrogens, but 2 are in the water, so the other 3 are left behind. And this is ammonia gas, which is very popular, very strong smelling gas. So these 3 gases are made as a result of these intermediates. These guys are unstable. As soon as they are made, they break apart, and you see the gases that are eventually made, which will produce bubbles or fizzing, and you have carbon dioxide, sulfur dioxide, and ammonia gas. Now, here we have a few examples. I'm going to actually go through each of these so you can get an idea of how this works. Okay? First, you're going to see the first one. There's not too much to do. I can actually do it on this page here. You got HCl and K2S. So what happens is the H and the S are going to get together. H is +1 and sulfur is -2, so you're going to get H2S. You just need to memorize that that's a gas. Just like when water's made, you put liquid, put gas for this one. And then you got K and Cl. K goes first because it's a metal. Cl is your nonmetal, so you make KCl upon crisscrossing. And then to balance, you got to put a 2 here to balance the potassiums, and you got to put a 2 here to balance the Cl and the H, and that's how we got the first example. Okay? Now, I'm going to show you the next 3 on the following page. So on the next page, we're going to go ahead and write HCl here. Notice we're doing the second one over here. So it's HCl and potassium carbonate. So what's going to happen here is same thing. You're going to have these 2 get together. So what happens is H plus and let me not put the plus sign. That'll be confusing. But the H and the carbonate ion are going to get crisscrossed. And when you crisscross, you get H2CO3. And then the other product is going to be K with Cl, and when you crisscross these 2, you get KCl. But here's the problem. This guy's unstable. So instead of that staying put, we saw that it's going to break apart into water and carbon dioxide. And you still got your KCl over here. And we'll go ahead and put HCl here. We'll put K2CO3 here. Okay, and then to balance this, we got 2 potassiums on the left, so we're going to have to put a 2 here to balance the potassium. And then we're going to have to put a 2 here to balance the chlorine as well as the hydrogen. And there is your first one. And here's your gas. Right here, we know this is a liquid. We know this is your gas. And this one's aqueous because it's an alkali metal is present. So that would be one of the first examples. Now let's take a look here at another one of those gas evolutions. We're going to use HCl again. So I can do this right here. I'll do this underneath here. So you got HCl. And this time it's going to be with potassium sulfite. So same thing's going to happen. We're going to have these 2 get together. And again, H is +1, sulfite is -2. So when you crisscross, here you get that unstable intermediate. And then when these two get together, you saw how I did this one earlier. This is just going to be KCl again. We already know this is going to be aqueous, but the problem is that he's unstable. So it's going to break apart. I'll actually split it like this. You know water is one of the products. The other product is going to be sulfur dioxide gas. So you now have 3 products instead of 2. Let's put a plus sign between them. So HCl and K2SO3 will generate the following 3 products. We know that this is a liquid. Here's your gas. There's your gas evolution. Then you got a KCl. And again, to balance, you got to put a 2 here to balance the potassium, and a 2 over here to balance the Cl and the H, and you have this one fixed. Okay? Now, we're going to take a look at one more. We have this one here with ammonium chloride, so we could see the other example, ammonium chloride with potassium hydroxide. So let's do this on a new page here. So we have ammonium chloride, and it's potassium hydroxide. So what's going to happen here is same thing. Let's follow the pattern. These two are going to get together. Now ammonium is +1, and hydroxide is -1. So when they get together, you simply get NH4OH, and that is your unstable product. You got to remember this. And then these two, since we've already done it quite a few times, just remember, always put the metal first, the non-metal second. You're going to get KCl. But this is unstable. This is your intermediate. So this thing is going to break up into 2 things. Okay, one of them, well, let's be consistent here. I've been showing you that you always make water. Okay, that's always been one of your products. And if you do the process of elimination, ammonia gas is going to be the other. So you got your liquid water, you got your ammonia gas. Let me go ahead and fix this up a little bit. And we still got KCl. We know that's aqueous because it's with an alkali metal. And then let's put the original reactants here so we can complete this and balance it. Okay, by the way, these are aqueous as well using your solubility rules. But if you look at this, this one actually is already balanced. So notice when it's a gas evolution reaction, you have to pay attention that, you know, with the intermediates, if it's H2S, that's automatically a gas. And then the other 3 come from intermediates. So when you have carbonic acid being formed, remember that that's going to split up and your gas would be CO2. So there's your gas there. It's made indirectly. And then you have hydrogen sulfite. Same thing. It's unstable. It's going to split apart. This time you're making sulfur dioxide gas. And then we just saw ammonium hydroxide. Same thing. Water is always the common product when it splits, but this one forms ammonia gas. And these gases were made as a result of these intermediates breaking apart. So at the end of the day, you have a double replacement reaction is not driven by a transfer of electrons. In order for a double replacement reaction to occur, one of the products has to be either a solid, a liquid, or a gas. If it's a solid, we call them precipitation reactions. If it's a liquid, acid-base reactions would be one of the most popular ones, and that liquid is water. Okay, and then the third one is when a gas is made. They're known as gas evolution reactions. The gas can either be made directly, like hydrogen sulfide gas, or the gas can be made indirectly as a result of an unstable intermediate breaking apart. Okay, but keep in mind that these guys do not fall under the category of oxidation reduction reactions.